All right. So what have we talked about here? What is a meromorphic function? This means analytic except at isolated singularities, right? Where each singularity is a pole, right? Right. So we do include like pole of order 0 in this way of speaking, all right? Like a pole of order 0 is what? A removable singularity, right? And remember we talked about at an isolated singularity, there are 3 different possibilities, right? There's the case you have a removable singularity, you can have a pole of order n for n greater than or equal to 1, right? Or you can have an essential singularity, right? And so what does this look like? What's this concept look like at infinity? Well, first of all, let's just say this. At z naught, not equal to infinity, it means your f of z looks like what? It looks like, it can be written as the sum, right, k equals minus n to infinity of, a sub k, good grief, sorry, a sub k z minus z naught to the k, right? And so that's like a sub minus n over z minus z naught to the n power plus dot 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 plus a sub minus 1 over z minus z naught to the first power, right? Plus a sub 0 plus a sub 1 times z minus z naught and so forth and so on, right? So this is what it means for a function to be meromorphic at z naught not equal to infinity. It means that it can be written, its Laurent expansion has finitely many reciprocal terms, right? And so this is what we call the principal part, right? Right. And the other piece is the piece which is just analytic at z naught itself, right? And so these, you could also identify these as the f0 and the principal part is the f1, the analytic part is the f0 of the Laurent decomposition we started with, all right? What does this look like at infinity? Then what we're talking about is f of z looks like something like, well, what that means then is g of z, right?
N is a number, right?
N is a number here, a fixed number.
So don't you just no minuses.
That's okay. So g of z is, rather g of w
Sorry.
is f of 1 over w. Yeah?
These terms cancel out, leaving you just with the ANs, like the minus AN and the AN, right? If you add them all. That's wrong too.
Oh, okay. So at infinity, we understand in terms of the function evaluated at the reciprocal being, so we define analytic at infinity to mean that f of 1 over w, which defined g of w, was analytic at w equal to 0, right? So w equal to 0 corresponds to z equal to infinity, right? And so, anyway, let me just forego this switcheroo here and just get straight to the point. What we mean by a function be meromorphic at infinity is that this formula holds, all right? Except the difference is you've got 1 over z minus z naught. Well, excuse me, 1 over z rather. 1 over z power k. So if you look at that, what that means is if you work this out, you've got a to the minus n, z to the n, a to the minus 1 z plus a0, and then you've got a1 times 1 over z, a2 times 1 over z squared, plus dot dot dot. So at infinity, to have a pole at infinity means that you actually only have finitely many powers, positive powers of z in the expansion. All right, so this right here is the principal part at infinity. So if you've got infinitely many of those sorts of things at infinity, that means you've got an essential singularity. So for example, if we look at, say, f of z is equal to, say e to the z. That's a simple enough one, right? This is equal to 1 plus z plus 1/2 z squared plus, 1 over 3 factorial z cubed, dot, 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 dot. So there are infinitely many positive powers of z. If we look at, like an exterior annulus, this is, it's for z in the complex plane, right? But certainly this is true for modulus of z, let's say greater than 1, just for the sake of discussion. Again, that's just for the sake of discussion. So that would be a neighborhood of infinity, right? If you look beyond 1, this gives you what we call a neighborhood of infinity, right? And neighborhoods of infinity are exterior to some circle, and on, right? So this is a neighborhood, this is the power series expansion, the Laurent expansion of e to the z at a neighborhood of infinity. This shows that infinity is an essential singularity of this function. So this implies that infinity is essential singularity for, f of z equal e to z at infinity, right? So this function is entire on the complex plane, right? Because its power series expansion converges for the whole complex plane, right? And yet, this function is not meromorphic on the extended complex plane because its isolated singularity, which is at infinity, is not a pole. It's an essential singularity. The same story plays out for all of our other favorite functions, like cosine, sine, sinh, cosh. All of these have infinitely many positive powers of z in the Laurent expansion of an exterior annulus. So they all have essential singularities at infinity. What does not have an essential singularity at infinity, which is interesting? Well, something like this, right? So if I had something like f of z equal to z cubed plus z squared plus 1 over z plus 1 over, 1 minus z. Well, let me make it simpler than that. Let me not burden us with algebra for this example, okay? Here we go. So this function, right? This function has two singular points on the extended complex plane. What are they? Z is equal to 0, right? Yeah, and z, I'll call it z1 equal to infinity, right? And so, oh, my bad. Let me make that a 13 instead of a 3 here. Yeah, 13. So at z equal to 0, we have pole of what? Pole of order 13, right? Because as you look at the part which is singular at 0, the most offensive thing there is the 13th power, right? So like 1 over z to the 13th is the most singular piece of that, right? It's not essential because there's only up to order 13 reciprocal powers at 0, right? Now at infinity, it's a pole of what? In this case, 3. So like z cubed plus z squared is the singular part. At infinity, all right? So this function has two isolated singularities, right? Both of which are poles. So this function is meromorphic on the extended complex plane. All right? There's a theorem that says, in fact, the only functions which are meromorphic on the extended complex plane are rational functions. So if you have a meromorphic function on the extended complex plane, you're talking about a rational function. So theorem f of z meromorphic on C union infinity, if and only if f of z is equal to, let's say, p of z over q of z, right? For some polynomials p of z, q of z. So let's see here. I think I'll prove for you guys the one direction here. Let's see here. So suppose, so the converse direction, right? Suppose f of z equals to p of z over q of z, right? Then what can we do? We can do long division, right? Then by division algorithm, right, there exist, let's say, q1 of x and r1 of x. Listen to me. Sorry, my bad. Z. q1 of z, r1 of z with the degree of r1 of z less than the degree of q of z, or r1 of z equal to 0, and f of z is equal to what? It's equal to q1 of z plus r1 of z divided by q of z. Now, so what are the poles? What are the singularities of this rational function? Where is it singular? It's singular wherever q of z is equal to 0, right? And also where else? At infinity, right? Because at infinity, what ends up happening is so I guess this isn't immediately obvious from what I have written so far, but yeah, fine, it's not entirely obvious yet with what we've done. Let's see here. Okay, so to prove this in detail, I need to give convincing evidence that everything in R1 of z divided by Q of z, when we expand on an exterior annulus, it gives us reciprocal powers, right? Whereas the positive powers on an exterior annulus are all coming from Q1 of z, right? So notice that at Q1 of z, at infinity rather, the principal part is Q1 of z, right? And so that's the polynomial piece here. And so since it's just a polynomial, it has finite order, so it's a pole at infinity. So the proof that R1 of z over Q of z has an expansion on an exterior domain, which is just reciprocal powers of z, it's going to take me a little work, given what we've done so far, I think, here. Let me try to tackle it with an example. Let's see here. So let's start with something relatively simple, like if I have, what example am I on? Example 3. So this example actually has value independent of the thing I'm working on the proof of, okay? So we'll come back to that, all right? So think about this one. What if I have 1 over, let's say, z minus z naught? I want to rewrite that in terms of reciprocal powers of z. How do I do it? Here's what I do. I go, well, that's 1 over z, right? 1 over 1 minus z naught over z. Right? Now it looks like a geometric series. So how's that go? Well, this is 1 over z times the sum, n equals 0 to infinity, of z naught over z to the n power. When is that true? When am I allowed to make that step? What condition is needed for the geometric series here to converge? We need that the modulus of z naught over z to be less than 1, right? In other words, we need that the modulus of z naught is less than the modulus of z. Or let me put it in a more natural way to say it. The modulus of z has to be greater than the modulus of z naught. So in picture, if this is z naught, right? And here's, here's 0. This is the circle of radius z naught. Then everything out here is where this formula is legit. It's an exterior annulus, right? And so, what's this say? This says that for every thing like 1 over z minus z naught that you get something that this expression right here, mind you, is analytic at infinity, right? Because it's got no polynomial piece. Does that make sense? I don't know if it makes sense or not, but it is the way things are at infinity. And it takes some everything's upside down at infinity in some sense, right? I mean, it's funny, but so we have z naught to the power n over z to the n plus 1. All right, that is a function which is analytic at infinity. Why is that analytic at infinity? If this is equal to f of z, right, then g of w equal to f of 1 over w has what? It's the sum n equals 0 to infinity of z naught to the n, w to the n plus 1, which is manifestly analytic at 0, right? So this is analytic at w equal to 0, which shows you that the original f was analytic at infinity. That's how we judge analytic at infinity. We look at the reciprocal function. Okay, great. So what does that matter? Because what is this over here? We have r of z over q of z. Well, check this out. Q of z, so let me return to the proof now, okay? Consider this. Q of z is equal to what? Well, by the fundamental theorem of algebra, which I think we proved, right? There's some constant. Let's call it c. And then you've got z minus z1, z minus z2, z minus z, let's say, what order do you want the denominator to have? It doesn't really matter. Let's say it has order s. All right? I know that we can factor z like this, right? And so if you look at it, we've got r1 of z, right, divided by a constant times z minus z1, z minus z2, z minus zs, right? And my point to you is we can use the algebra of partial fractions, right, to rewrite that as a sum of reciprocals. See, this can be rewritten as something like a1 over z minus z1 plus a2 over z minus z2 plus plus a sub s over z minus zs. This is by partial fractions algebra, right? Or was that part of the Calc 2 you guys skipped?
No, I remember partial fractions.
You remember partial fractions?
That's part of integration.
How about you, Jade? You remember learning about it? Yes.
Also, it's in
It's also in DEs? This is true. But it's easier here because we're in complex, right? So we don't have that like in differential equations and also in calculus 2, we have to give a much longer discussion about partial fractions because sometimes you got to do the quadratic piece, and sometimes the quadratic piece got a repeated root. Sometimes it's got a, you know, oh, maybe do I have to mind the repeated roots here as well? I may be getting a little bit too nonchalant here about that. Oh, I think the repeated roots matter here. Don't let me sell you this. But we still have to care about repeated roots. But for the sake of the simplicity of the argument, just for the moment, let's assume that all the roots are not repeated. There is a way to deal with repeated roots. I'll show it to you in a second, okay? So it is true. The partial fractions decomposition in general would also have to include terms like 1 over z minus z1 squared, as many as you need to, you know, whatever the multiplicity is of your first root. So here I'm assuming that these roots are distinct, which of course I have no right to do in abstract, right? So here, just for simplicity of understanding, for the moment, for conversation's sake, we're supposing z1, z2, zs distinct. I'll talk about what we could do. I'll deal with the possibility that they're repeated once we get through this part, okay? So my point to you is we can take this, we can write it like that, right? And every one of those, if we're on an exterior annulus, what can we do? We can rewrite these using this example 3. Well, this is just, you know, the sum A1, right? Sum n equals 0 to infinity of, you know, z1 to the power n over, what? Z to the n plus 1, right? And then you get A2, right? Sum n equals 0 to infinity z2 to the n over z to the n plus 1, right? And so on down the line, right? And, well, is this okay? I mean, wait a minute. You mean to tell me you're going to do not 1, not 2, but s applications of the geometric series? Yeah, I'm saying that. And so what condition do we need overall for that to hold? If you think about that, we need to be exterior to, we have to be beyond the modulus of z naught. I mean, we have to be, z has to be what? Modulus of z has to be greater than, right, the max of the modulus of z1, the modulus of z2, and so forth. Modulus of zs, right? But certainly we can do that, right? If we're looking for a neighborhood of infinity, we can make it as far out away from the origin as we want, which is to be closer to infinity, right? And so we can get all of these conditions on a neighborhood of appropriate neighborhood of infinity, right? So if my rational function has a denominator with distinct roots, we have shown such a rational function is meromorphic. See, because what's the deal? Well, this shows a couple things. Number one, it shows the partial fractions decomposition shows what? It shows, on the one hand, that when we look at infinity, we've got all of the polynomial powers wrapped up in q1 of z, right? And the rest of the things in r1 over q of z, those are analytic at infinity. Every last one of these is analytic. The sum of analytic functions is analytic, right? How about the poles? What's the order of each pole? Finite pole. What's the order of each finite singularity for f of z under this?
The nth?
Like, what is the order of, what is, I'm claiming z1 is a singularity of f. What's the order of the pole?
Would not be whatever the subscript of z1 is? First.
Well, actually, z1, z2, zs,
Yeah,
they're all the same answer.
Well, if it doesn't, do they all go out to infinity? That means they don't have an order, right? Because you know, when we did the order over here on E2.
Look, let me make it more simple. So f of z is equal to 1 over, you know, well, a1, as I've called it, over z1, z minus z1, right? Plus everything else.
Yeah.
And all of everything else, well, what is everything else? Everything else, if you want my formula, here it is. It's f of z minus this one, okay? So that's just a lazy way for me to write everything else. But this piece, what is in here? What's in here is the q1 of z, which is polynomial, and then these guys.
Yeah.
Those, maybe I should look at it this way. It's all of these things, right? And the f of z, excuse me, and the q1 of z.
Yeah.
Those are all analytic at z1.
Didn't we say q, the degree of q is greater than the degree of r, so it's whatever the degree of q is?
Degree of q. The degree of r1 of z is greater than, is less than the degree of q of z.
Yeah.
Yeah.
So the pole would be order q.
Oh no. My point to you is that, okay, so let me recap here. At z1, the only piece which is singular is this.
Yeah.
Everything else here is analytic because the singularities are isolated. I've assumed that these are distinct, which means the singular part of the function at z1 is just this. So it is a pole of order 1. In fact, assuming that the denominator has distinct roots is to assume that every pole in your rational function has order 1. So in this special case, we have a proof of the, this direction of the theorem, right? The converse direction. What would happen if you had like a repeated root? How would that go?
We ordered whatever how many times it's repeated.
Yeah, let me sort through it here. Can I erase? So let's look at example 4. How do you deal with z minus z naught squared? What's that? So, do you guys remember how we did geometric series tricks in Calc 2?
I have no tricks.
You know tricks?
Yeah, I know them now.
So how can I get that to a reciprocal power? Do I differentiate it? Do I integrate it? What do I do? If I call this thing, f of z for the sake of discussion.
You want to get to a reciprocal power?
Yeah, if I do what? I integrate, right? Integration raises the power.
Oh, yeah.
So the integral of f of z dz is equal to the integral of dz over z minus z naught squared, which is what? Minus 1 over z minus z naught. Am I right?
Yeah.
All right. Aha! Well now, hooray, geometric series to the rescue, right? So we're looking to find an expansion on the exterior annulus. So we want to divide by z.
I thought you couldn't imply that if you have big F of z, that big F of z doesn't imply analytic on F prime, or little f of z. Like, where do you say that the other one there? Like,
What am I? I'm just using the geometric series.
yeah, I know, but like, what does that tell you about F prime?
Well, we'll see. So this is what? This is the sum, right?
Yeah.
N equals 0 to infinity of minus 1 over, well, let's say minus z naught to the power n, right? Over z to the n plus 1, just getting to the point. Now that is not, it's like this is not the series you're looking for, right? But it's close because if we differentiate this, we get back where we want, right? So we So the derivative, so f of z should be the derivative with respect to z of this guy. And the good news is that because these Laurent series are uniformly convergent on their, on their homes, which are annuli, yeah, we can commute the order of differentiation and summation and be okay. Because we have that uniform convergence, which leads to, in fact, normal convergence on these annuli, which allows us to make this step. And so that gives us, minus the sum. Here, the n equals 0 drops out, I think. Well, I gotta be careful here, I better not. N equals 0 to infinity minus z naught to the n, that's still there, but then I've got times n, well, excuse me. What's the power here? That is z to the minus n minus 1, isn't it? That's the power. Because we've written reciprocal. So that's actually, minus n minus 1. N plus 2, yeah. Because we have to decrease the power by 1 by differentiating, right? Yeah, so but the minuses cancel, which is nice. I somehow got another minus out here because I'm a doofus. All right, you only get to use your minus once. So, turn that frown the other way. Let's see here, n equals 0 to infinity. Z naught to the n times n plus 1 over z to the n plus 2.
Looks like what we had before.
It is similar, but now there's an n plus 1.
Yeah.
But the point is, that is analytic at infinity. All right? And so if we had a repeated root in our denominator, the partial fractions decomposition would land us to things like this, but that's no problem because at infinity those are analytic. All right? So what about a triple root? What happens then? What do you do with a triple root?
Probably like n plus 3.
You have to integrate twice, right? So you integrate twice. You integrate twice, you apply the geometric series result, then you differentiate twice to get back, and you'll get a similar result. All right? So similar calculations show that, 1 over z minus z naught to whatever power you like, let's say m, is equal to the sum n equals 0 to infinity of z naught to the whatever times some number, all right, over z to some power n plus, I don't know. I'd have to work through it to give you those details, but I think it should be clear that it's just going to, the same kind of calculation is going to go through. We're just going to get a function which has no polynomial piece at infinity. Yeah. So that's essentially the proof of the converse direction here, right? If we have a rational function, then if you examine its expansion at infinity, you've got a polynomial piece, and then all the pieces which are divergent at finite points, those give you analytic pieces at infinity, and vice versa. At a finite point, in the partial fractions expansion, the part of the partial fractions expansion which is with respect to that 0, that's the part that's singular. Everything else is analytic. How would the other direction of this proof go?
Forward direction.
Yeah, the forward direction. What would that look like?
So we have a meromorphic. Oh, it's meromorphic.
Yeah, f of z is meromorphic, right?
Yeah. So you get all the nice properties. Like you don't have to. What is it?
So so first of all, if Well, there's some kind of tricky stuff that has to go on here a little bit because I'm thinking through it here. I guess I could actually look at my notes and use the proof there, right? But
If it's meromorphic, you get
so first, let's just if it's meromorphic, that means that if you pick Z naught, like suppose Z naught is one of its singularities, all right? That was supposed to be singularity. Then that means that f of z is, a sub minus n, z minus z naught to the n, right? Plus dot 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 plus a minus 1 over z minus z naught, right? Plus what? A0 plus a1 times z minus z naught plus dot 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 dot. And that's a rational function. Now, okay, so there's the rub. Like, this is unending, you see? So for us to see that this is a rational function, I need to know that I can rewrite this as the fraction of two polynomials. This is not immediately obvious, is it?
Or can you just say it has to be finite?
Well, yeah. Here's the key is that the number of poles has to be finite. So the proof is on page 137. I think we're getting shy and short on time here. I think we actually may be out of time, but let me just get the main points in the proof here. So on page 137 of my notes, it says f of z a meromorphic function on C star. C star is this, Jade, my notation for this is usually this, C star. That's tacking on infinity. I said the number of poles of f must be finite, otherwise they would accumulate to give a singularity which is not isolated. Ooh. So if f is analytic at infinity, then we would define p infinity of z to be f infinity. Otherwise, f has a pole of order n, and p infinity z is a polynomial of order n. In both cases, f of z minus p infinity of z is analytic at infinity, with f of z minus p infinity going to 0 as z goes to infinity. And so actually what I do to find the rational function that the function's equal to, I use the fact that there has to be I look at the pole at infinity and just basically work backwards from there. See, because the mess is, if you look at a finite singular point, then all of this is somehow getting the Taylor expansions around the other singularities. So you have to somehow rip that apart to pick off the piece which is actually, it's complicated if we look at a finite point. If we look at infinity, though, the argument's given on page 137, which gets you through it. Okay, so anyway, listen, guys, I have a few pages of notes on partial fractions decomposition. I don't think I'll spend class time on that too much. And I mean, if you want to, I can go through some more calculations on this kind of thing if it's helpful. Is this helpful? Do you want to see more of these sorts of calculations? Because otherwise, I'm just going to go ahead to the residue theory next time. And we can circle back to this and do more of this if you guys get confused about it in the homework or whatever. But does that sound good? So with that, my intention next time is to start the residue calculus, which is chapter 7. And we'll look at the residue theorem, and we'll learn a couple of simple rules for calculating residues. It's not really that different than what we're doing right now, but all of a sudden we'll be integrating things that you couldn't integrate before, so it's pretty neat.